Hello, everyone. My name is Fernando Gama, and I am currently a postdoctoral scholar at the Department of Electrical Engineering and Computer Sciences at the University of California, Berkeley. First of all, I would like to thank Guy, who invited me to take part of this workshop. This talk is, let's say, a simple introduction to some of the elementary results regarding the theory of graph neural networks. In particular, I will focus on two different ways of approaching the problem. The first one is when we want to do graph classification, and therefore we are interested in knowing when a GNN can tell apart two graphs. The second one, which arises when processing graph signals, is kind of the opposite, because we want to guarantee that the GNN will behave the same even if the graphs are slightly different. The first approach was pioneered by Xu, Hu, Leskovec, and Stephanie Jagielka in ICLR 2019. I relies on the Weisfeiler-Lehmann test. I will briefly overview it, and I will do my best to address all the questions you may have about it, but of course I won't be able to give the full picture in the same way the authors could. The second approach is the one we have developed with many of my colleagues, of whom I would like to thank now, and relies heavily on the notion of graph frequencies and the spectral domain of graph signals. So, in any case, my hope is that this talk could serve as the starting point for all of you to start looking into this very exciting problem of theoretical foundations of graph neural networks. Thanks, Guy, once again for the invitation, and thank you all for attending. This talk focuses on machine learning on graphs. And the reason why we care about machine learning on graphs is because graphs are genetic models of signal structure that can help to learn in several practical problems. For example, in data arising from citation networks, where we consider each paper to be a node, and the graph is used to describe the citations among all those papers. The objective of a semi-supervised problem is to classify these nodes according to the field they belong to. In recommendation systems, we have these graphs where nodes are movie ratings and edges represent rating similarities. These graphs can be used to learn a prediction of the rating of unseen movies. In authorship attribution, we have networks with nodes representing words and edges whose strength represents how often a certain author uses those pairs of words. As it happens, different authors use pairs of words with different frequencies. It follows that these graphs are different for different authors and can thus be used to learn the authorship of unattributed texts. Other examples involve physical networks, that is, graphs that arise from physical connections between nodes, as it happens often in biological data. Or also, as we see in this video, we have these robots that need to coordinate their velocities to fly together while avoiding collisions. The graph describes the communication network, and we want to leverage it to learn distributed controllers. As a final examples, we have smart grids, where each node is either a consumer or a generator, and the grid has to keep the balance between the power generated and the power consumed. This balance is determined by a highly nonlinear system dependent on the actual topology of the grid. Thus, the graph representing the grid topology is useful for learning power generation schemes. These are quite dissimilar problems, but that all require information from the graph structure in order to be successfully solved. Thus, the core of machine learning on graphs is about exploiting the graph structure. In particular, we will focus on graph neural networks, which can either be described generically as an aggregation step followed by a combination step, or as a graph filter followed by a nonlinear function. Both of these descriptions are equivalent, it just allows for different perspectives on the architecture. The objective of this talk is to introduce and present some basic theoretical properties that GNNs have. We can classify the techniques to develop theoretical properties in three big groups. First is the work by Hu, Wu, Leskovec, and Jagielka, which focuses on the task of graph classification and thus wonders about the capability of a GNN to tell apart two different graphs. The workhorse of this approach is to leverage the similarity between GNNs and the Weisfeiler-Lehmann isomorphism test. I will briefly introduce the basic concepts surrounding this approach, but I apologize in advance as I won't be able to present this work as well as the authors would do. The second approach focuses on the notion of processing graph signals, which are defined on top of the graph structure, and thus the objective is quite the opposite. We want the GNN to yield the same output when processing the same graph signals as long as the underlying graph structures are similar. The key tool for this approach is to carry out a frequency analysis of GNNs. Finally, although I won't be covering this in this talk, we have graph scattering transforms. In this case, the graph filters are replaced by banks of graph wavelets that are carefully designed instead of learned. Knowing the wavelets and tailoring them to the particular application allows for a very deep analysis of the behavior of these scattering transforms. Guy Wolf is an expert on this subject. We'll start by briefly defining what a graph neural network is, to fix notation and the like. But before that, let us fix what graph structure data is. A graph G consists of a set of nodes V and a set of edges E connecting those nodes. We can represent this graph structure by means of a matrix. For example, the adjacency matrix that assigns a 1 in the ijth entry if and only if there is an edge connecting node I and node j. Another example is the matrix Laplacian, whose diagonal elements are the degree of each node, that is, the number of edges attached to each node, and where the off-diagonal elements are the negative of the adjacency elements. Note that the Laplacian can only be defined for undirected graphs, and the undirected graphs will lead to both symmetric adjacencies and symmetric Laplacian matrices. Also, note that when we adopt this matrix description of the graph, we are fixing a given ordering of the nodes. A mapping between all different orderings is given by the use of permutations. From now on, we will refer to a generic matrix called S to describe the graph. The S comes from support matrix, that is a matrix describing the graph support, or from graph shift operator if you are familiar with the graph signal processing literature. We also consider that the data is described in terms of node features or graph signals. That is, we have a value associated to each node. For example, we associate a vector of dimension f to each node, and we can collect all of these features in a matrix of size n times f, where n is the number of nodes. Note that each row corresponds to all f values at each node, and we call these values features. Operations on the features of each node can be carried out individually for each node. The columns, on the other hand, correspond to what is known as a graph signal, that is, the collection of the f feature across all nodes of the graphs. Operating on the columns implies exchanging information across different nodes, so we need to be careful that when we operate on the columns, we are respecting the topology of the graph. The key component of a graph neural network is a graph convolution. Graph convolutions are generalizations of time convolutions, so let me take the license to remind you all about regular convolutions. A convolution is a linear combination of shifted versions of the signal x. We shift the signal through time, and for each shift, we weigh by a different coefficient h. If we want to extend this concept to graphs, we need to have a notion of shift. This notion of shift is given in graph signal processing by the support matrix S. We see that we can describe this time signal as supported by a graph that is a directed path. Note that if we apply the adjacency matrix S of this graph to the signal x, we are indeed shifting the signal in time, or equivalently, shifting it around the graph. So the traditional notion of shift in time is equivalent to applying the shift S of a graph. Let's consider an arbitrary graph now. Here we have this graph with 11 nodes and the different signal values on top of the nodes of the graph. Each time we apply the shift, we are gathering information from nodes that are farther away. The first image here is x, and the second image here is s times x. In red, we are showing the nodes that node 1 can reach by successive applications of the matrix S. Here is the second application of the shift, and the third application of the shift. For each different application, we weigh the resulting signal by a different coefficient or filter tap. Here we see the same effect on a larger graph, where the colors represent the signal values and the bigger disks represent the nodes that are reached by successive applications of the shift. So a graph convolution is a linear combination of shifted versions of the signal. In essence, the graph convolution is assigning different weights to information located in different neighborhoods. The effect of the shift operator is to update the signal with a linear combination of neighboring values. Thus, this operation is entirely local. Certainly, a graph convolution is equivalent to the application of a linear shift invariant graph filter, so I will use both terms, convolution and filtering, interchangeably. When we consider the convolution operating on f-dimensional node features, we simply extend the convolution operation. Recall that the convolution has to be a linear operation that depends on local information accessible only by means of neighboring exchanges and that has a distributed implementation. The extension of the convolution can be seen in this equation here. To see why this is the case, let's analyze it step by step. Let's start with s times x. We have x, which is the collection of our f-dimensional node features, where each column is a scalar graph signal representing each feature, and we have s, which is the matrix representing the sparsity pattern of the graph. For example, the adjacency matrix or the Laplacian matrix. We see that the multiplication of x by s on the left is actually shifting each graph signal feature. We are taking each row of s and using its entries to compute a linear combination with the entries in each column of x. Since each column of x is the scalar graph signal representing each feature, and since each row of s respects the sparsity of the graph, what we're actually doing is a linear combination of the values of each feature in neighboring nodes. So we are indeed shifting each of the columns as SXF indicates. Now let's consider the matrix H. This matrix replaces the scalar filter type that we used to use in graph convolutions. When we multiply x by h on the right, we see that we are doing a linear combination of features at each node. That is, we take each row of matrix X, which corresponds to all f features at each of the nodes, and do a linear combination of them with the entries of the filter tab in each of the columns. Note that when we multiply by a matrix on the right, we are doing linear operations that do not involve any neighbor exchanges. They are computed internally by each node. So now we see that this operation is, in fact, the appropriate convolution operation for dealing with multi-feature graph signals. Note that this convolution operation is equivalent to the application of a bank of graph filters. So, a graph convolutional neural network, which we refer to simply as GNN, but in a more nuanced discussion of architectures should actually be referred to as GCNN, builds upon the convolution operation as discussed in the previous slide, adds a pointwise nonlinearity to the processing pipeline, and repeats in cascade for L layers. We define the GCNN as a function phi that acts upon the input node features X and is parameterized by the support matrix S and the filter tabs contained in the set H. There are many popular GNN architectures that use convolutional filters and can thus be explained as particular instances of this expression here. If all the eigenvalues are different and set the value k here to be n-1, then this architecture spans the same representation space as the spectral GCNNs introduced by Bruna in ICLR 2014. If we set S to be a normalized Laplacian with eigenvalues between -1 and 1, and we set the filter tabs hk to be computed recursively by means of the Chebyshev polynomial, then we get the Chebnets by De Ferrar et al. In EURIPS 2016. So far, these two architectures are equivalent in terms of representation power for the specific given S, as the GCNN we have introduced so far. Other popular architectures further restrict the representation space by imposing more conditions on the filters. For example, the diffusion CNNs of Atwood et al. Look at single-layer GCNN with filters of order 1, where the filter tabs are forced to have the same value across all rows. The popular GCNs of Keefe and Welling consider only filters that collect information from immediate neighbors, and, even more so, they force the filter tab for the 0th order polynomial to be the same as the filter tab for the 1st order polynomial. Imposing this condition automatically forces the learned filters to be low-pass filter. However, it is important to emphasize that if we relax the impositions that the 0th and the 1st order coefficients have to be the same, then we can learn high-pass filters even if we gather information from one-hop neighbors only. SGCs by Wu et al. Set an order of polynomial k greater than 1, but force all filter tabs for orders below this big K to be 0. This also forces SGCs to learn only low-pass filters. These architectures further restrict the representation space by learning specific kinds of filters only. In any case, we know that the GCNN description here describes all of the graph neural networks with convolutional filters, and thus the results discussed in what follows are applicable to all of them. So once we have set up our GCNN architecture to process graph structure data, we learn the best filter tabs H from data. GCNNs are useful in 3 kinds of problems, which entail 3 different ways to look at data. The graph signal processing approach is the closest one to traditional CNNs, and in fact, GCNNs in this context act as a direct extensions of CNNs. In this case, we consider that each element in our training set is a matrix n times f, and that each of them is described by a graph S that is given and fixed. S describes the problem, but the actionable variable is the graph signal on top of it. In the popular problem of semi-supervised learning, each element in our training set is the f-dimensional node feature, so each data point in our training set represents a node in the graph. So the graph has the size of the samples in the training set. In this case, it is important to note that the samples in the training set are not IID, but are related by the graph structure S. Finally, in graph classification, every element of our training set is a different graph, given by a set of node features in the matrix X and by a different matrix description S. Note that the size of the graph need not be the same, but the number of features has to. These clearly different problems can all be approached by adopting a GCNN architecture, which speaks volumes to its flexibility and power. After this introduction to GCNNs, and hopefully after some clarifications that set the notation straight, let's go to the first of the theoretical approaches that I would like to discuss today. As I have mentioned a few times already, consider this to be just a minimal introduction to the principles behind one of the most popular approaches to developing theoretical properties of GNNs. The work by Xu, Hu, Leskovec, and Jagielka, establishes a theoretical framework for analyzing the representational power of GNNs. Their objective is to characterize the ability of a GNN to distinguish different graph structures. This, of course, makes total sense in the context of graph classification. We want to be able to know when two of the graphs in the dataset are actually different, or, put it differently, we want to know when using a GNN will fail in recognizing that two graphs are different when they actually are. To achieve this, the authors consider the problem of graph isomorphism that asks whether two graphs are topologically identical. And to attack this problem, they consider the Weisweiler-Lehmann test. This WL test is a computationally efficient test that distinguishes a broad class of graphs. Not all graphs can be distinguished by this test, but a very broad class of graph topologies can. The WL test works by iteratively aggregating the features of nodes and their neighborhoods and mapping them to new features. Then the test concludes that two graphs are non-isomorphic if the new features between the two graphs differ. The authors realized that the WL test is analogous to the neighbor aggregation step in GNNs. Thus, they were able to prove that GNNs are at most as powerful as the WL test in distinguishing graph structures. In particular, the authors established the conditions on the neighbor aggregation and graph readout functions for them to be as powerful as the WL test. And they present a novel architecture, the Graph Isomorphism Network, GIN, which is then proved to be as powerful as the WL test. Therefore, the authors conclude that if we use GINs, we would obtain a maximally powerful architecture that is able to distinguish the same class of graphs that the WL test can. So essentially, a maximally powerful GNN maps two nodes to the same output, the same embedding, only if they have identical neighborhoods and identical node features. The authors formalize this in the following theorem. Let phi be a GNN with a sufficient number of layers L, then phi maps any graphs G1 and G2 that are different under the Weisweiler-Lehmann test to different embeddings, as long as, first, the function that aggregates information from neighborhoods is injective, and second, the function that maps this aggregate information to a new feature space is injective as well. So, as we can see, the authors found out that injectivity is the key to obtain a maximally powerful GNN. The authors further characterize all injective functions and propose the Graph Isomorphism Network, or GIN, as the one that learns this injective function by using a multi-layer perceptron, a fully connected network, thus leveraging the universal approximation theorem. We can see that the resulting GIN is a GCNN with order 1 polynomials, and where the MLP at each layer can be realized by concatenating a series of graph filters and pointwise nonlinearities with order 0 polynomials. This paper by Xu, Hu, Leskovec, and Jagielka offers the seminal work for characterizing the ability of a GNN to distinguish different graph structures by leveraging the Weisweiler-Lehmann test. One of the few observations that the authors mention in their work is that these results hold for features belonging to a countable set, since injectiveness characterizes the distinctiveness of the inputs. If we consider uncountable sets, then the results require more care. Another important aspect that the authors mention is being left as future research is to further characterize how close the resulting features are for different graphs. Finally, I would like to bring your attention to two other research groups that have been also looking at the problem of using the WL test to understand GNNs. These are the groups of Soledad Bichar, now at Johns Hopkins, and the group of Will Hamilton at McGill. But of course, this is not an exhaustive list, and every conference there are submissions looking into this problem. So this is certainly a very active area of research. Now, for the second way of understanding GNNs, we're going to look at kind of the opposite problem. In graph classification, we want to know whether our architecture, the GNN, can actually distinguish graphs. When we consider the graphs as given, for example, from the physical description of the problem, as is the case of multi-agent robot teams, or power grids, or sensor networks, then what we want to know is that if the graph changes slightly, or if we don't know the graph and we have to estimate it, or if the graph changes slightly from training to testing, then we want to know if our GNNs will still output the expected results. In other words, we want that if the graphs are similar, then the outputs will be similar. We will show this by proving two properties of GNNs: permutation equivariance and stability, or more formally, Lipschitz continuity to the graph structure. That is, Lipschitz continuity to the matrix S, not to the input X. Recall that the graph convolution operator is a polynomial on the shift operator, which depends on the filter parameters h, on the shift operator s, and is applied to the input signal x. Then we have that graph convolutions are equivariant to permutations. This means that for graphs with permuted shift operators and permuted graph signals, it holds that the outputs are permuted versions of each other. The proof follows from basic algebra and the properties of the permutation matrix. Since GNNs are a cascade of graph filters with pointwise nonlinearities, and since a pointwise operation does not mix node values, then GNNs retain the permutation equivariance property. This is stated formally in the following theorem. For graphs with permuted shift operators and permuted graph signals, it holds that the output of one GNN is a permutation of the output of the other GNN as long as they are using the same filters H. Essentially, this means that signal processing with graph neural networks is independent of labeling. Now, permutation equivariance is fairly straightforward and kind of expected. It is just the proof that if the ordering of the node changes, an ordering that we chose arbitrarily when we decide to describe the graph by a matrix, then the output of the GNNs changes correspondingly. But on a deeper look, we note that the invariance to node relabelings allows GNNs to exploit internal symmetries of graphs. Consider the two pictures shown here. As we can see based on the labeling of the nodes given by the numbers, these two graph supports are exactly the same, which means that the matrix S that describes both graphs is the same. What is different is the graph signal defined on top of them, which is shown here in colors. The graph signal in A is different from the graph signal in B, that is, the vector x are different. However, we can take the signal in B, rotate it 180 degrees, turn it inside out, and we end up with a signal that looks exactly like the signal in A. It's just the labeling that is different. That means that, although different, signals on A and B are permutations of one another. Permutation equivariance, then, means that the GNN can learn to process B from seeing A, leading to faster training by leveraging structure to learn multiple scenarios from a single sample. Permutation equivariance is an important property because it allows for GNNs to explain the graph structure and generalize better. And while real graphs don't usually exhibit perfect symmetries, they might still have substructures that are close to permutations, as we will see shortly. Now, the thing is that permutation equivariance is a property of graph convolutions inherited to GNNs. Then why bother in adding pointwise nonlinearities to create GNNs? Or, more concretely, what is good about pointwise nonlinearities, and similarly, what is wrong with just linear graph convolutions? Briefly, the problem with linear graph convolutions is that they can be unstable to perturbations of the graph if we push their discriminative power. The advantage of adding pointwise nonlinearities is that they make GNNs stable to perturbations while retaining discriminability. These questions can be better answered with an analysis in the spectral domain. A graph convolution is a polynomial on the support matrix. We can decompose the support matrix S as V lambda B Hermitian to write the spectral representation of the graph convolution as a projection of the output on the eigenbasis of S. We see then that the graph convolution is a pointwise operation in the spectral domain due to the diagonal nature of the matrix lambda here. This operation is determined by the graph frequency response, which is a polynomial on each eigenvalue lambda I with the same filter taps hk. We can reinterpret the frequency response as a polynomial on continuous lambda. Here we have in black solid line the value of the polynomial throughout the spectrum, and in blue dots what's the value that the frequency response takes when instantiated on a specific graph with eigenvalues given by the blue ones here. If the graph changes, the eigenvalues change, and the places where the frequency response gets instantiated change, as indicated here in red. However, the frequency response as a function of continuous lambda, this black solid line, is the same and hasn't changed. So the key insight here is that the frequency response is the same no matter the graph. The actual effect of the graph on the output is observed when instantiating this frequency response on the particular spectrum. Of particular interest are graphs that we call integral Lipschitz. These are graphs whose frequency response satisfies that lambda times its derivative is less or equal than c. Integral Lipschitz filters have to be wide for large lambda because if lambda is big, then the derivative has to be small, and thus the filter cannot change fast. But they can be thin for low lambda so that the derivative can be very big and still satisfy the integral Lipschitz condition. This means that the filters can change fast for low values of lambda. These filters are of interest because they are the ones that are stable to perturbations. What perturbations? Well, we measure perturbations as the relative distance between the original graph S and the perturbed graph S hat. We define it as the norm of the smallest matrix E that maps S into a permutation of S hat. Note that this distance measures relative differences between graphs modulo permutations. In particular, it is small if the graphs are close to being permutations of each other. Now, we can get a stability result when the GNN consists of filters that are integral Lipschitz. Consider a GNN with L layers having integral Lipschitz filters HL with constant C. Graphs S and S hat are such that their relative distance is less or equal than epsilon over 2. Then it holds that for all signals X, the difference in the output between a GNN that runs on S and one that runs on S hat, both GNNs with the same set of filters H, is bounded by epsilon, which is the distance between S and S hat. In essence, GNNs can be made stable to graph perturbations if filters are integral Lipschitz. While the GNN stability theorem holds for any relative error matrix E, the particular case of edge dilations provides valuable insights. In edge dilations, we multiply edges by a 1 plus epsilon for a small epsilon close to 0. An edge dilation just produces a spectrum dilation, an increase of epsilon in the eigenvalues. As we see in this image, small deformations may result in large filter variations for large lambda if the filter is not integral Lipschitz. We see here that the output of the filter changes a lot for large eigenvalues when moving from the blue eigenvalues to the red eigenvalues. And if the output changes a lot due to a change in the graph, then it is certainly not stable. Integral Lipschitz filters are always stable, and this is because either the eigenvalue doesn't move or the filter doesn't move. The problem with linear graph convolutions is that they cannot be simultaneously stable to deformations and discriminate features at large eigenvalues. Integral Lipschitz filters are stable because they are wide for large eigenvalues, which are the ones that tend to move a lot. But this means that if we want to separate between frequency content located at eigenvalues that have a large value, then we do not need a filter that is flat for this part of the spectrum, but actually filters that can be narrow enough to separate one eigenvalue from the other one. But if the graph changes, even if it changes slightly, then the eigenvalues fall outside the filter's passband and thus the output becomes 0. So, in summary, linear graph filters cannot be simultaneously stable to deformations and discriminate features at large eigenvalue. This limits their value in machine learning problems where features at large eigenvalues are important. The good thing about pointwise nonlinearities is that they preserve permutation equivariance while generating low graph frequency components, which we can discriminate with stable filters. Here we see that when we apply a ReLU nonlinearity to the sole eigenvalue that we had before, now we have low eigenvalue frequency content. And this low eigenvalue frequency content is different from the one generated by the signal on the other eigenvalue. So now that we have low eigenvalue content, we can design stable filters that will be able to separate them, because low eigenvalues do not change much when the graph changes. So in summary, the nonlinearity demodulates. It creates low frequency content that is stable. Therefore, GNNs are stable and selective information processing architectures, whereas linear graph filters are not. So we saw that graph convolutional neural networks are built from graph convolutional filters followed by pointwise nonlinearities. To better understand their theoretical properties, we discussed two different approaches. First, from the perspective of graph classification, we want the GNNs to have different outputs if the graphs are different. The work by Xu, Hu, Leskovec, and Jagielka tackles this problem by leveraging the Weiss-Feiler-Lehmann test to characterize the ability of GNNs to discriminate graphs. From a graph signal processing perspective, where the underlying graph support is given, what we want is the GNN to have similar outputs if the graphs are similar. Through a frequency analysis, we proved that GNNs are both permutation equivariant and stable to changes in the graph support, and that the inclusion of pointwise nonlinearities creates frequency content throughout the spectrum, making GNNs both stable and selective information processing architectures. I hope that this has helped spur your interest in the possibilities of doing research in the theoretical foundations of GNNs, and that maybe you can even come up with novel ways of tackling this issue. Thank you very much for your attention.